Hey guys, welcome to your first HSC Physics investigation. Today we'll be talking about using a pendulum to determine acceleration due to gravity. Your school might look at the use of computer-assisted technology, but it's very unlikely to be asked in the HSC just due to different socio-economic statuses of different schools, and some may have limited access to computers. So we're looking at using a pendulum to determine the value for acceleration due to gravity on the Earth. So just really quickly talking about the experiment itself, which you're going to have to set up at school. Firstly, you need to construct a pendulum at least 1 meter long. So you'd get about a 1.5 meter long piece of string, but you would fix it at different lengths. So your first length should be around about 1 meter. Then you might go up to 1.1 meters, 1.2, 1.3, 1.4, 1.5. You need to attach that to an appropriate support, so something like a retort stand with a clamp. And you need to tie an appropriate mass, around about 50 to 100 grams at the lower end, to act as a pendulum bob. So the reason why we use something of length at least 1 meter is to ensure that the period of the pendulum is relatively large. You're going to make mistakes in terms of your reaction time, measurement errors, etc., etc. But we want to spread them out over a longer period. So in order to spread them out over a longer period and have less of an impact on our results, we need to ensure that the length of the string is longer also. Now the purpose of the mass itself is just to provide tension inside that string, so we need a force in order to make that pendulum oscillate. So that 100 gram or 50 gram mass, which is tied to the lower end to act as that pendulum bob, ensures there's tension in the string, which ensures that the mass is able to undergo a form of simple harmonic motion. So when you guys actually do the pendulum itself, you've got to make sure that you measure the appropriate length. So the length of the pendulum is measured from the point of attachment to the center of mass of its bob. So usually in most questions we assume that the mass itself is a point source. So that meaning the mass has no length. So the length of the string is the length of the pendulum. Whereas when you guys do it in the lab, you're not going to be able to use a point source. You're going to have to use a mass that has some length, and the length may be significant, especially if you're using one of those slotted masses with a hook. So you've got to make sure that you measure the appropriate length, and the appropriate length is from the center of where it's attached. So that's around about up here. So if we count up, so we've got 55 centimeters here, 55 and a half, 56, 56 and a half, 57. So around about 57 and a half centimeters. Now down here we need to measure to the center of its mass. So some people would measure to the bottom of its mass. So there's our 10 centimeters there and 10 and a half, and they say that the length of the pendulum is from 10 and a half to 57 and a half, so it's around about 47 centimeters. But we need to measure to the center of the mass, which would be somewhere around about here. So rather than measuring to 10.5 centimeters, we have to measure somewhere up here. This is around about the center of the mass, so we say that's about 12 centimeters there. So the length of the string is the length from the point of attachment up here at about 57.5 centimeters to the center of the mass down here, which is about 12 centimeters. You need to ensure when you conduct this experiment that the angle which you create with respect to the vertical is relatively small. So we generally say less than 15 degrees deviation from the vertical. I might suggest less than 10 degrees just to be safe. It requires a mathematical approximation which only holds true for a very small set of angles. So we're using a relationship between sine theta and theta in terms of our unit circle. So the relationship which we're talking about is sine theta is equal to theta, which again is only true for really small angles. So if the initial angular displacement of the pendulum is small, we can use this small angle approximation, which enables a simple equation for period of pendulum to be derived. So you do not need to know the derivation of this equation unless you do your extension 2 math. You can do it then, that's fine. But this equation is not in your formula sheet. However, I have seen questions before which have asked you to recount a method that you use to determine acceleration due to gravity by using a pendulum. If you aren't familiar with this equation because you're relying on it being in your equation sheet, then you're unable to get full marks in questions such as that, because you need to be able to rearrange this equation to make G the subject and then talk about how you actually solve for G. So this is pretty much what your experimental setup should look like. So you've got a retort stand with an appropriate clamp attached. You have a piece of string being tied to that clamp with a mass or mass carrier being attached to that string. You've got the string being displaced at an angle of less than 15 degrees from that vertical, and you've also got a counterweight on the base of your retort stand to ensure that your retort stand does not shift during the oscillation of the pendulum. When doing the pendulum experiment, we need to make sure that the results we get are as accurate as possible to ensure that our value of acceleration due to gravity is accurate and valid. So when we use a stopwatch, we time at the extreme of the pendulum's motion rather than when it's in the middle going its maximum velocity. So essentially we're timing when the amplitude of the pendulum is the greatest. So we're timing 10 full swings back and forth, so back and forth being one full swing, we're timing that 10 times. We then divide this by 10 to get the average period of motion. Now the reason why we do that is, let's get a scenario where we have a reaction time of 1 second, and the period of the pendulum is also 1 second. So if we're timing one single period, the error within that single oscillation is up to 100%. Now if we time for 10 periods, which is 10 seconds, that 1 second reaction time error is now decreased to a 10% percentage of measurement error. So that makes our results more accurate. So this averaging technique tends to minimize errors, as does timing the extremes of motion. So as you can see, there are many assumptions in this pendulum experiment, and there are 3 more which we should mention just for good measure. So the first assumption is that there is no friction or air resistance, so there's no retarding force acting on the pendulum. Second thing is that the string is massless, inextensible, and always remains taut. So if the string had mass, it would also contribute to the oscillation of the pendulum. For simplicity's sake, we assume that it is massless. We're also assuming that it's inextensible, which means it's non-elastic, so the length of the string does not change. If the string is elastic and the length of the string changes throughout the period of oscillation, then the equation becomes a lot more difficult. We also assume that the string remains taut, so the tension in the string is uniform. Third assumption is that motion only occurs in 2 dimensions, so it's tracing out the path of an arc rather than an ellipse. You'll find when you actually do this experiment, it's extremely difficult to keep it in 2 dimensions, and it will trace out an ellipse, but we will assume that that path is an arc. So going over some key terms that we use in our experiments, our independent variable, or the thing that we change during this experiment, is going to be the length of our pendulum. So we might change it from 1 meter to 1.1 meters to 1.2, 1.3, 1.4, and 1.5 meters. So our dependent variable, or what we're measuring, so we're measuring the period of the pendulum. So more precisely, we're measuring 10 times the period of the pendulum to reduce errors in the measurement of the period. And our controlled variables. So controlled variables are things that are kept constant throughout successive trials to ensure that the results are fair. So some examples of our controlled variables are things like mass of the pendulum bob, the initial angular displacement, and the initial pendulum velocity. Our next step is to set up an appropriate data table. So here is an example of an appropriate data table. We've got 4 columns. Our first column being the length of the pendulum. Our second column being our T10, which is the time taken for 10 swings back and forth. Our third column is our period, and our fourth column is our period squared. So we use some values for our length of pendulum. So we said something around about 1 meter, followed by 1.1, 1.2, and 1.3, and 1.4 meters. Now our T10, so again that's time for 10 periods. So in order to convert that into period, all we need to do is divide by 10. To get from period to period squared, all we need to do is square the value in that third column. So let's just use some numbers for an example. So let's say for our length of pendulum, 1.4 meters, we have a T10 of 15 seconds. I'll then divide that by 10 to determine period, so I get a period of 1.5 seconds. I'll then square that value to determine my period squared as 2.25 seconds squared. So note that the unit for period squared is actually seconds squared, not seconds. The significance of the use of period squared will become apparent over the next few slides, and when we do some data analysis for our pendulum experiment. The aim of this experiment is to find a value for acceleration due to gravity. So we need to work out a way of determining this value from the data which we're taking from our investigation. So our first thing to do is to use our pendulum equation. So we've got period is equal to 2 pi square root L on G. So T is our period, L is the length of our pendulum, including the length of any mass or mass carrier or to the center of the mass. G is the acceleration due to gravity, which we want to find out. So our first step is to square both sides. So I come up with an expression T squared is equal to 4 pi squared L on G. We then need to rearrange that to make G the subject. So we end up with an expression G is equal to 4 pi squared L on T squared. From these results, we need to make an appropriate graph. This is where we use our value of period squared. We actually plot a graph of period squared versus length of the pendulum. Period squared is to be plotted on the y-axis, and the length of the pendulum is to be plotted on the x-axis. So from this, when we determine the gradient, again, we must use 2 points, and those 2 points must line our line of best fit. We then must use a gradient triangle to show our determination of the rise and to show our determination of the run, and then from that to show our determination of the gradient. Going back to our expression, so G is 4 pi squared L on T squared. From our graph, the gradient of our graph is going to be T squared over L. Therefore, the inverse of the gradient is L on T squared. So 1 on gradient is equal to L on T squared. We can then separate our expression for acceleration due to gravity in 2 parts. So we've got 4 pi squared, which is a constant, times L on T squared. Now we just said that ln t squared is the inverse of the gradient, so we end up with 4 pi squared times 1 over gradient, or 4 pi squared over gradient is going to give us our value for acceleration due to gravity.